In this module, we will discuss further details and examples of free body diagrams and forces. So the first thing that we'll categorize again is a smooth surface. We talked about this already a little bit, but let me say again, a smooth surface is frictionless. And if we isolate, in this case, the box, which is on that frictionless ramp, and we draw the reaction, we understand that that would be a normal reaction perpendicular to the surface, no friction, and I'll picture the action as pushing on the bottom of the block, because typically one hard surface can push on another hard surface. It doesn't pull unless it's magnetized or somehow in something like a track, so unless that was indicated, we'll assume pushing, not pulling. And one more time, I'll remind you that frictionless is an idealization which does not exist in real life. You as the engineer have to decide when that is and when that is not an acceptable assumption. Now, rough surfaces, on the other hand, do allow for friction. So we'll isolate the block. It still has the normal force, but it also now has additionally a frictional force. And the frictional force is always parallel, but you might have seen some rules about friction in physics, for example. Friction is quite a complicated topic, and we will not really be doing a full treatment of friction until the A level of this course. But for now, let me just say that you might have heard the law F equals mu times N. This is only true for dynamic or kinetic friction, but in general, that's not always the case. And what's also a complicating factor is that in some problems, you don't even know which type of friction you have at the beginning, if it's static or kinetic. So for now, in this level of the course, we will assume that I will give you the state of friction that you have to deal with. And let me just say, don't always write F equals mu times N unless that is specifically indicated. Okay? So for example, if I draw this body with friction, I might say that if it's static friction, I just draw that force as some unknown reaction, and I'll just call it F. And maybe we don't even know which way it's going. In this case, I've pictured it pushing upward, but it turns out that you would be equally correct, certainly at this level of the course, to draw the frictional force in the other direction. What we'll see later is that eventually you would write equations and you'd solve for those forces. And if you had your force in one direction initially, you'd get one answer. And if you did it in the other direction, you'd have the negative of that answer, and that would be equivalent. And we'll see that later when we get to that point. But for now, just realize that you can draw the friction in either direction you want, unless there's something specific to tell you otherwise. I also want to get into what's called a dual contact surface. This is somewhat of a more complicated situation, but imagine that you have a collar going around a frictionless track, and you isolate that collar. Depending on what's actually happening, it could turn out that the normal force of the track on the collar is exerted on the inside of the right wall, but it could also be that in a different situation, that normal contact is occurring by pushing on the inside at the left wall. So these are both correct assumptions, and again, later on when we solve equations, we would determine how the answer of the equation dictates which one it was. But for now, at this point in the course, you would be okay to draw on either side. But we don't usually draw both at the same time because there's never such a thing as a perfectly tight contact. There's always some tolerance, and for different reasons that we'll see later, we'll assume that only one of the surfaces is in contact and the other one is not. The next set of categories I'll introduce are what I'll call the straight axial elements. And here we have three different varieties, cables and ropes, bars, struts, and rods, and springs. And I'm putting these all in the same table so you can compare the similarities and differences. So a cable, for example, can carry only tension, But a bar or a strut or a rod could carry tension or compression, and also a spring could carry tension or compression. A cable is typically straight, but it can also wrap around a curved surface like a pulley. It does not stretch, however. The cable's length does not change. A bar also does not stretch or contract. It does not change its length, whereas a spring is designed to change its length, so it does stretch or contract. If you look at the pictures here, we see intuitively what we've talked about before is that the forces transmitted along a cable or a bar are parallel to themselves. That's also going to be a true assumption of a spring. And in the case, again, of the cable, we see the tension should be pulling. Cables can support tension but not compression, whereas the bar could support either a tension or compression, and the same with the spring. Now, one thing I'll also point out is that if the cable is wrapping around the pulley, and the pulley is frictionless, then the two tensions on either side are the same, and that will be our common assumption. Later on in our chapter on friction, we'll see how the two tensions might be different, but for now we can assume that T1 equals T2. And let me emphasize again that in all cases, the forces are transmitted parallel to the element. And later on we'll see that this is due to another assumption, which is that each element is approximately weightless. And such elements will also later be classified as two-force bodies. And to give you a taste of that, notice if I put these two blue dots on the cable segment, there's really 2 points where that cable is being contacted. One is at the anchor point at the hinge at the top, and one is at the bottom where I have a force being applied. So that's 2 points of contact, two-force body. The same with the bar. I could illustrate there are 2 points touching that body, and so that's another way of saying two-force body, and the same with the spring. And the reason the weightlessness is important is because if there were a weight on those bodies, then that would be a 3rd point, and thus that would be a 3-force body and not a 2-force body. So that's a little taste of what you'll study a bit more in detail when we get to that point. Now, one more thing about springs. Many of you might have heard of Hooke's law already. And Hooke's law is a statement about how does the force relate to the way that the spring stretches or contracts. So let's suppose I have a spring initially of a length L0, and I'm going to draw a reference line which says S is equal to 0, which means that's the line compared to that line where I'm measuring the displacement. So if, for example, I really stretch the spring, I now see the spring looks longer, and the right point of the spring moves to the right, and that's in the zone of S being positive. And Hooke's law says F equals K times S, which means the force is proportional to the distance that I stretched it. It's not F equals K times L, it's K times S. And again, L0 represents the initial, what we call the relaxed length of the spring, and the L is the total length, which is the L0 plus the S, meaning the stretched length. You can also have compression. Now this diagram looks a little bit different, or possibly even problematic, because you might say, how is it that the spring is contracting and yet I'm still drawing a force and tension, especially since in the last slide we took the trouble of drawing the forces showing compression. Well, the reason in this case is because when we're using a law like Hooke, we want to have one standard way of writing an equation. So I still want to use the same equation, F equals K times S. What makes this work is that in the second case of compression, the S is now a negative number. It's now to the left of my reference line. It's in the opposite direction of positive S. So if I now say that I have K times a negative value of S, I get a negative force. And what you've already learned in vector resultant module is that if I have a negative value pulling to the right, that's the same as a positive value pushing to the left. So Hooke's law does work for both tension and compression with one law. We don't need a separate law for the tension and compression cases. So this is a bit something that you want to get used to, because again, I do acknowledge it looks a little bit different, but this is the way I recommend thinking about it. Another thought I thought I'd share with you is what actually counts as a spring. You know, you might have a real mechanical spring of the kind we just saw. You can buy them in a hardware store and so on. But many other kinds of objects that have deformation can be modeled as springs. So for example, this little molecule, you could actually model a molecule with having some flexibility, and you could model that by a spring law, of course, at the microscopic or even smaller level. A cushion, when you sit down, deforms, and so you could think of the cushion as a spring, because as you put your weight on it, the more weight, the more contraction happens in the cushion. A beam acts as a spring. The more you put a force in the middle, the more it deflects in the middle. You could model that as a spring. Paperclip. This is actually a rotational spring in one sense, but you could think about the more force that you apply with your finger, the more the paperclip is going to deform. And even an orange or something else like that, or a ball, as you squeeze it, it deforms. So the harder you squeeze it, the more it deforms. And I'll have you ask, what else can you think of? Are there other examples of things that you have seen or played with or worked with that can be modeled as springs? So let's do an example before we close this module. Let's suppose I give you this example of a collar at point A, which can slide up and down a pole, and it's also attached to a spring. And I ask you to draw the free body diagram of the collar. So I'm going to draw you the collar, and first of all, remember that word isolate. I'm isolating the collar away from everything else. I'm drawing the collar and only the collar. And so, as we saw in the earlier module, we want to start asking some questions, such as, what is touching or acting on this object, and where is that happening? So the first thing we'll say is that we already see in the diagram there's a force called F. So I'm going to say that that force is given to me, and that must be drawn, and that's kind of obvious. But let's make sure we account for that, and we'll do that one first. Now, the next thing you could say is that the spring is also contacting the collar, and it's contacting the collar also through the center at that black dot. I'm going to assume first that the spring is pulling, the spring is in tension. So let's say the spring pulls on the collar, and I'll represent that force as if it's pulling on the black dot. And I'll label it FAB, because in this case it goes between points A and B. Now, what else is also touching the collar? Well, the pole is touching the collar. This is a little bit tricky in a sense, because the pole is now touching it from the inside. So we should draw the detail to show, in fact, that the collar is hollow inside, and those dashed lines represent the inside edge of the wall. And I'm now going to estimate or postulate how is it that the pole is going to be interacting or acting on this collar. As we discussed earlier, when we have two solid surfaces touching on each other, unless they're magnetized or glued or welded, they can push but they can't pull. So in this case, I'm going to assume that the pole is pushing on the inside wall of the collar. And then the question is, which way should I draw it? Well, a hint is, even though we have not studied efficiently equilibrium of forces yet, you can think about, since the spring has a component horizontal to the left, it would be reasonable to assume that the pole force will counterbalance that. So I'm going to assume that the force of the pole on the collar acts on the inside at the right wall, and it pushes, so that force is pointing to the right. And I'll call it N for normal. Now also, because I didn't give you a full statement of the problem, maybe this problem has friction, maybe it doesn't, so sometimes you'll have to decide that based on what is given to you. But let's in this case say if there were friction, I could also show the friction, And again, the friction is being caused by the pole on the collar, acting on the inside. In this case, I'll, just for the sake of argument, assume the friction is acting upward. And maybe the weight is not negligible. Again, in this problem, we were not told, and so maybe in some cases you would neglect the weight, in other cases you might not, and so I'll draw that as another option. And as you reflect on this, notice again that there's a lot of questions and judgments to be made, and this is the kind of the skill building we want to do, because sometimes a problem statement will be very clear and very explicit. Other times it will be deliberately leaving out some details to leave you to make some good judgments. Ultimately, again, in engineering, you are going to be expected to make good judgments. Now, having said this, there are some other things that we could think about. Again, the force F was given. I'm not going to change that. But imagine the spring maybe was in compression, not tension. It could be pushing on the collar. So another possibility is, instead of drawing tension, I could draw compression. That would be an equally valid assumption unless I knew for sure from some other information that I had tension. If that's the case, I might want to reconsider at which point the wall, at which point the pole is touching the inside of the collar. And because now my spring is having a component pushing to the right, I might therefore change my mind about how I draw the pole touching the inside of the collar, and now I'll have it pushing to the left. I'll still call it N, but now the arrow points to the opposite side. And again, the frictional force maybe still is going up, and I'll draw it like that. It's possible the friction might be going down. That's another possibility, and I'll leave you to think about that, but I won't redraw that. Okay, so this is a taste of how we would draw a free body diagram of an object with some degree of complexity where you have to make various kinds of decisions. Another possibility I could have given you is the same system, but now I say draw the pole, CD. And this one I'll leave you to try, but again, here are the key questions. Isolate the pole, so I'll do that for you. What is touching or acting on the pole? At what points do these actions occur? And how do you express those actions with forces or torques? And I'll say you can refer to the previous tables of reaction types as a hint. So you might look at the end of the pole, for example, and ask yourself, what do those symbols represent? And can you take your best guess of interpreting from the reaction table what is acting on the end of that pole? And I'll ask you to also think about what else is touching the pole, and we'll talk about that in class.